Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Capillary Viscometers, Errors and Corrections. However, before going into the details of today's lecture, what we will have a recapitulation of what we have studied in the previous lecture, and then we see an example problem based on what we have seen in the previous lecture. Okay. So, in the previous lecture we have seen different details of capillary viscometers, and then when we apply or when we use such capillary viscometers for measuring the rheology of non-Newtonian fluids, especially for time independent non-Newtonian fluids or generalized Newtonian fluids, we have developed what are the corresponding equations for shear stress and shear rate. That is what we have seen. So, what we have found by doing the simple analysis and derivation, we have obtained shear stress for the fluid whose rheology is tried to measure using the capillary viscometer is nothing but tau w is equals to minus delta p by L r by 2, and then shear rate 3 n prime plus 1 by 4 n prime 8 v by d, that is what we have seen. Remember this shear stress and then shear rate we are measuring at the wall, and then we have seen the details y at the wall, and then what about the variation with respect to the r position, and all those things we have seen, and then we develop these equations. Okay. So, in this shear rate equation, n prime is nothing but d log tau w by d log 8 v by d, or when you plot tau w versus 8 v by d on a log plot and then get the slope of that line, that slope is nothing but n prime. That is what we have seen in previous lecture, right. Otherwise, what we further understood, like if you wanted to know the shear stress of the unknown fluid that have been tested using capillary viscometer can be obtained if you know the pressure drop that has been applied to get a certain flow rate, right. So, that is, if you know the pressure drop, you can easily calculate the wall shear stress. Similarly, if you know the volumetric flow rate for that pressure drop, then that volumetric flow rate, from there you can find out the average velocity, and then once you know the average velocity, you can find out the wall shear rate. And this shear rate, whatever 3 n prime plus 1 by 4 n prime 8 v by d is there, it is nothing but the true shear rate for a time independent non-Newtonian fluids or generalized Newtonian fluids. Remember, all this analysis we have done for time independent non-Newtonian fluids only. Okay. And then we have also seen this, whatever 8 v by d is there, that is nothing but the nominal shear rate or apparent shear rate, which is a true shear rate for Newtonian fluid, but not for time independent non-Newtonian fluids. For time independent non-Newtonian fluids, 8 v by d is a apparent or nominal shear rate, and then if you multiply that 8 v by d by a correction factor 3 n prime plus 1 by 4 n prime, then you get the true shear rate. This is what we have seen. Now, we take an example problem. However, before taking the example problem, we see a few modes of operation of capillary viscometers. Now, what are you measuring experimentally in capillary viscometers? You are simply varying the pressure drop and then obtaining the volumetric flow rate. Those are the measurable quantities, right. Those measurable quantities you are further modifying or using such a way that you can get the shear stress and shear rate information. That is all different things. But in order to have a kind of constant flow rate or constant pressure drop, so you can have a different modes of operations, right. So, that is what capillary viscometers, constant flow rate versus constant pressure capillary viscometers. That is what we see, what are the difference, and then which one is more reliable, which for what kind of fluid, which kind of mode of capillary viscometer is better, those things we see now. So, constant flow rate devices, here what we have a container, right, or reservoir or vessel, whatever you call. So, right. So, here to this bottom there is a opening is there, that opening is such a way that can be adjusted, and then a capillary can be fixed of different diameters, right. It is not a fixed opening, it is an adjustable opening here. So, at the bottom you can attach a capillary, right. To this container there is a load mechanism is provided, so that you can provide certain pressure or certain load you can provide, so that to get the required flow rate, right. This is one mode of the operation. So, now you apply certain load and then you get obviously certain flow rate, right. So, now in this device what you want to have a constant flow rate and then accordingly the load you will be changing. Why? Because let us say gradually when you are doing experiment, so then the fluid, whatever that unknown fluid that you have taken in the reservoir or the vessel, that will be consumed and going out as a flow rate, as a fluid, right. So, then obviously this quantity volume is going to reduce. So, then obviously the load, if you are keeping fixed, so then the flow rate is going to change. So, the monitoring or the operation you will be doing such a way that you will maintain the constant flow rate and accordingly you change the load, right. So, that is what this constant flow rate device is, very simple, and these are suitable usually for highly viscous melts, resins and then thick suspensions. Right. Obviously, you know that if you are maintaining constant load or constant pressure drop, you cannot have a constant flow rate, because the material, whatever the head is there, the material head is there, that is going to decrease gradually. So, then accordingly your flow rate is going to decrease. So, accordingly there is another mode of operation is possible. You maintain constant pressure you maintain, and then whatever the flow rate is there, that flow rate you can collect it. Right. So, for here you have a pressure gauge. The similarly entirely operation is very similar. What you have a reservoir, right, and then to that bottom of that reservoir you have a opening. That opening is a adjustable opening, so that you can change the so that you can fix a capillary of different diameters like this, right. But in addition you will be having a pressure gauge and that you will be using some gas cylinder, so that to maintain the pressure, required pressure. So, here what you are doing, you are maintaining constant pressure, and then whatever the flow rate you are getting, that you are noting down. So, whether you use the constant flow rate device or constant pressure device, ultimately what you are getting, you are getting pressure drop versus volumetric flow rate information only you are getting. In one case you are fixing pressure drop fixed, in one case you are keeping pressure drop fixed, another case maybe volumetric you are keeping fixed, right. So, but anyway this is the ultimate data that you are going to get, which you will be using to get the shear stress and shear rate, as we have already discussed. Then it is constant pressure devices are usually suitable for low to medium consistency fluids. However, it has been found that constant flow rate devices are more appropriate for different operational reasons. And then pipe viscometers having straight section of pipe are used in industrial setting for quick measurements, as I already discussed in the previous lecture, that pipe flow is a very common phenomena in any of the process industries wherever the fluids are flowing. So, if you wanted to know instantly the rheology or the viscosity or apparent viscosity of the fluid under operating conditions or under pressure or for a given pressure drop and then volumetric flow rate, you can have a kind of slit kind of thing within that pipe at different locations, and then periodically you can collect the flow rate and then measure the rheology for a given delta P versus flow rate information. Okay. Of course, depending on the nature of the fluid, safety precautions and all those things anyway will be coming into the picture. So, but that is basically it is possible to have pipe viscometers in real life industrial settings as in situ viscosity measurement devices. Let us say in your case, your fluid viscosity has to be maintained. Sometimes if you are allowing suspensions to flow through pipe, what happens, some of the particles may be settling at the bottom and those kind of things, such kind of problems may be there. And then because of that one, local viscosity may be different from the bulk viscosity, right. So, you have to have a monitoring of such viscosity if required, if it is essential property in your process streams or final product, depending on situations. So, if it is required, so then you can have a pipe viscometers inline in your process flow situations. And whether it is a constant flow or constant pressure device you operate, ultimately what you get volumetric versus pressure drop or vice versa data for different lengths and diameter of the pipes. Okay. That you convert in terms of given so called shear stress and shear rate, and then you plot them and get the rheology of the fluid. Now, we have an example problem to understand how to use these equations of shear stress, shear rate in order to know the rheology of a fluid if you are using capillary viscometer, right. So, that is what we are going to see now. So, following capillary viscometer data on high pressure polyethylene melt at 190 degree centigrade have been reported in the literature. Obtain true shear stress versus true shear rate data for this polymer. The true word is specifically used because we know there is a case like apparent or nominal shear rate information that you may get in general from this from the capillary viscometer, but we do not want apparent shear rate or nominal shear rate, but we want true shear rate. And then also mention assume end effects are negligible. What are the end effects? That flow has to be fully developed. In order to flow has to be fully developed, you have to have large L/D ratio capillaries, those things we have seen, and then under such conditions also at the entrance and an exit you may not have the fully developed flow. So, that may lead to some kind of error. So, it has been stated in the problem that you avoid or neglect such kind of effects. In fact, our next topic is to incorporate and then make necessity corrections for such kind of end effects only. Data is given 8V by D versus tau W, right. So, for generalized Newtonian fluids or time independent non-Newtonian fluids, whatever we have studied in the previous class, tau W is nothing but the true shear stress. So, we do not need to make any change in these values, that is already given. So, that is a given tau W information is a true shear stress information, but 8V by D information whatever is given, it is nominal or apparent shear rate for the case of generalized Newtonian fluids or time independent non-Newtonian fluids. It is 8V by D is true shear rate only for the Newtonian fluids. So, what we have to do? We have to do 8V by D multiplied by 3n prime plus 1 by 4n prime we have to do. That means, for each data we have to find out what is n prime and then multiply this 8V by D values with 3n prime plus 1 by 4n prime values correction. If it is a Newtonian fluid, so then this correction is going to be close to 1, approximately close to 1 if the fluid is Newtonian. But if it is non-Newtonian, if it is time independent non-Newtonian fluids, then definitely this n prime is not going to be coming close to 1. So, then obviously this correction is also not going to be close to 1. So, that we have to check now. So, how do we get this n prime? N prime is nothing but d log of tau W divided by d log of 8V by D. So, tau W 8V by D information has already been provided. So, on a log plot what you can have? You can have a tau W versus 8V by D curve whatever the data is given, and then at different tau W values you draw a line. You draw a line tangent and then find out the slope of the curve at that particular point, that we are going to see now here. So, tau W is this one, that is true shear stress for GNF, and then true shear rate for GNF is this one, we have already seen, right. So, n prime, this correction we need to make in order to get the true shear rate or correct the nominal shear rate, we need to have this correction 3n prime plus 1 by 4n prime, and then n prime is nothing but this one. So, what we are going to do? We are going to have a plot, log plot on tau W versus 8V by D. Let us say at this point of tau W, if you wanted to measure what is the n prime value, then what you do? You draw a tangent at this point like this, right, and then you find out the slope of this tangent line, that is nothing but your n prime. Let us say you wanted to measure the n prime value when the tau W value is coinciding at this point. So, at this point what you have to do? You have to draw a tangent like this very carefully and then find out the slope of this line. So, that would be giving your n prime value for this tau W. So, that you do. So, then for each tau w value n prime has been found out. That corresponding to each tau w value, what we have done, we have plotted a tangent at that point on the graph of tau w versus 8v by d curve, and then corresponding n prime value we have found for all the cases. And then you can see here the n prime is less than 1, and then as tau w increasing, it is further decreasing. That means higher shear stress, if you are increasing the shear stress or increasing the shear rate, it is becoming more shear thinning kind of thing. N prime less than 1, that means it is a shear thinning, and then that shear thinning behavior is increasing with increasing the shear rate or shear stress. Further you can see the correction. So, this gamma dot w is nothing but 8v by d multiplied by the correction factor 3n prime plus 1 by 4n prime. So, without taking the this correction into the account, the shear rate is 8, but now after incorporating this correction, it is 12.5. You may be thinking only 2.5 seconds, second in 2.5 second inverse only, but it is nothing but 25% difference. 12.5 minus 10 divided by 10, that is 2.5 by 10 multiplied by 100, right. So, 12.5 minus 10 divided by 10, okay, multiplied by 100. So, then it is coming roughly 25%. And then if you go to the other extreme, 2000 is the apparent shear rate, but but the true shear rate is 3113 second inverse, such huge difference. You can see it is almost like more than 50% increased. Okay. So, it is almost like 55% is increased here, shear rate. Okay. So, now whatever this tau w versus gamma dot w, this information is there, that is the true shear rate versus true shear stress information. Whatever this 8v by d is there, it is nominal one, because n prime is not equals to 1 or even close to 1. It is very different from one value of 1. Okay. So, this is how you can analyze the information that you get from the capillary viscometers. Okay. Now, we see sources of errors while using the capillary viscometers for measuring the rheology of non-Newtonian fluids, especially non-Newtonian fluids. That is what we are going to see. So, actually for that we have to do what we have to do, we have to enlist, are they these sources of errors, whatever we are calling, are they important, really so much different? What we have taken assumption is the fully developed flow, laminar flow, steady flow, right, and then incompressible fluids. These things we have taken into the consideration. While taking this fully developed flow, what we have taken, that L by D, we have taken large value, more than 100 or 150, something like that. So, that means if you take L by D or individual L or D such a way that if L by D is less than this thing, FD fully developed flow is not going to maintain. So, is it really going to have a kind of influence on the data, that we have to see. That means, if you change the L by keeping D constant, or by keeping L constant and then you change the D, or simultaneously when you keep changing L and D. So, are you going to get minus delta P versus Q information very different from one case to the other case? That is what we have to see. If you are getting different information, different data by changing the length of this thing, that means it is having this parameter is very much essential, and then we have to make a corrections for this L and D issues, right. And then another thing that we are saying, that laminar flow only. So, what if the capillary viscometer, the pressure drop you maintain such a way that the volumetric flow rate is very large. So, then the flow may not be laminar always. So, it may be turbulent also. Is it going to incur some kind of error? That is what another thing that we have to see. So, flow rate, right. So, what we understand from these, especially this fully developed flow and in laminar conditions, this L, this D and then this Q are having large influence on the overall rheological measurements that we are going to do and that we are obtaining by using the capillary viscometer. So, how much are they important? Do we really need to worry? Are these things, these are the only things that are important for us? There may be other errors also possible. So, what are the possible sources of errors in capillary viscometers that we first enlist, and then out of which what we do qualitatively we check which is more important, which is less important, so that we can neglect. There may be some errors which are causing very less influence on the overall rheology of the system. So, then such kind of errors we may overtake, we can just avoid. There may be some errors which may not be small, so then we have to make appropriate corrections. So, that is what we are going to see now. Sources of errors in capillary viscometers. Possible errors in measuring the rheology of a unknown fluid by capillary viscometers may have several errors, right. When you try to measure the rheology of a unknown fluid, rheologically unknown fluid, to know its rheology by using capillary viscometers, then several number of errors are possible. What are they? Entrance and exit effects or end effects. How much it is important. So, whatever the fully developed flow, what we have seen that we have taken this capillary, we have taken a capillary as a kind of circular pipe. That is how we have taken. How we have taken? We have taken L by D large, and then we said fully developed flow. This fully developed flow may not be there at the entry and then exit levels. At the entry, the flow will not be fully developed flow, and then at the exit also the flow will not be fully developed flow. But all our analysis is based on this one, fully developed flow, right. So, fully developed flow in the sense, in the flow direction the velocity is not going to change, whatever the velocity component, let us say z component, that dou Vz by dou z is going to be 0, or the pattern Vz as function of r, that if you plot, it is not going to change, whatever the pattern is there, that is going to remain same at different locations in the z direction, within the fully developed region, So, this we know from our transport phenomena also. So, but your analysis you are taking only for this consideration, but there are some reasons in that region this constraint is not valid. So, obviously that what is the effect that we have to see. So, one effect is that when the flow is not fully developed, usually pressure drop increases. Pressure drop increases at the entrance. At the entrance, pressure drop may increase if the flow is not fully developed. Indeed, it is not fully developed. So, what does mean by entry? So, we have this capillary viscometer arrangement like this, right. So, at this location, at the entry location, you are not going to have fully developed flow, right, and then this capillary is very large, that is what we are saying, though we are drawing very small one. So, this at the exit level again the flow is not going to be fully developed flow. These are the locations, exit locations. So, when at the entry location, obviously because of the sudden contraction of the flow area, it is because this is all flow, that is the fluid present here, suddenly the flow, whatever the cross section is here there, when you open the valve to get the flow rate coming out through the capillary. So, then sudden contraction of this cross section is taking place, because of obviously the pressure drop is going to be increased at this location. So, how much it is increasing, that we have to find out, and then from your true delta P you have to subtract that correction, whatever the entry level, the pressure drop, increased pressure drop. So, let us say 15 Pascal, it is showing, it is the entry at entry level, the pressure drop is 15 Pascal more than the average pressure in the fully developed region. So, whatever the data that delta P versus Q that you get, from the delta P you have to subtract this one, that is what we are going to see, right. So, since this fully developed flow it is causing some kind of error in pressure drop. So, corresponding changes would occur in the shear stress calculations, right. Shear rate is not going to be changed, because in shear rate we are going to have this V velocity which is coming from the volumetric flow rate. So, correction is required only in pressure. So, then correction is required only in the shear stress. That is the one. But exit also, the flow fully developed flow may not be there, but that contribution of this decrease in pressure drop at the exit point is not going to have a much influence on the rheology of the fluid, because it has already passed through the fully developed region mostly, right. Whereas the entry point, it has not yet entered the fully developed region. Okay. So, that is the reason it is more effective. Entry point pressure effects or increased pressure drop is going to have a more influence on this end effects. End effects is a combined term. One is entrance effect, another one is exit effect. At the entrance, what is the pressure drop? At the exit, what is the pressure drop? And then how much different are these values from the fully developed region pressure drop? So, overall pressure drop that we get in the capillary viscometer experimental study, that is the fully developed pressure drop, because we are taking L by D sufficiently large values. Okay. That is one. Then wall slip effect. What we have seen at the capillary wall at this inside locations, the velocity whatever is there, that we have taken as 0 in our analysis, isn't it, right. But in general, when you are taking non-Newtonian viscous fluids, the velocity is not 0, it may be having some different velocity compared to the 0 velocity. So, that also incurring some kind of effects in the rheology, right. So, since it is showing effect in the velocity, so then corrections would be there in the shear rate, not in the shear stress. Okay. That is also in detail we see, right. Then kinetic energy losses, what happen when the fluid is accelerating from this barrel or vessel to get into the capillary and then get out of the capillary. So, there is a kinetic energy loss, obviously, how much it is important. Then when the fluid is going out, so the head is fluid head is gradually decreasing. So, then fluid head, when it is decreasing gradually, so then how much is it going to have effect on the rheology? That is the other thing. Then departure from laminar conditions, your flow rate you are measuring, but corresponding to that one, what is the Reynolds number? You are not measuring actually, because you cannot measure also, because you do not know nature of the fluid. If it is Newtonian, so then Reynolds number definition is different. If it is shear thinning, so it is different, and then different in the sense different parameters n prime, m prime would be coming into the picture, right. So, that is the reason so you have to see without calculating the Reynolds number, how can you have a kind of a priori information from simply minus delta p versus q plot, so that you can understand whether the flow is in laminar conditions or turbulent conditions, because our all analysis is for the laminar condition only. If it is deviating from laminar condition, so that will again induce some kind of error. So, that is another error that we are going to discuss. And then viscous heating, obviously as we discussed, most of the non-Newtonian fluids are multi-phase components. It is not single component kind of thing, but most of the non-Newtonian fluids, it is not true for all the cases, but majority of non-Newtonian fluids are a kind of multi-phase flows, where some particles or bubbles, drops are suspended, like particulate systems, emulsions, suspensions, etc. So, when you have these kind of multi-component system passing through a very narrow gap, because narrow gap we are maintaining so that the changes in the shear rate or shear stress should be negligible. That is the reason we are taking the narrow gap. But when these material are passing through such narrow gap, especially high viscous materials are passing through narrow gaps at high velocity, high viscosity, high velocity, then that means high flow rate, then obviously viscous heating would be there. So, are you accounting for the viscous heating or not? If you are not accounting, that is also going to change the rheology of the fluid, or that is also going to show a different rheological parameters compared to the true rheological parameters. So, these are some of the possible errors. Right now, before going into the details of each and every error, so what we see, can we avoid some of them? right. So, obviously as engineering students we try to reduce our work. Can we avoid some of them? On what basis? Blindly we cannot avoid. We can have a kind of a qualitative estimation, which is important, which is less important kind of thing. If you cannot avoid, can we make certain kind of changes in the design or operational conditions so that certain kind of these errors may be reduced, if not all. So, either of the options we can see. Okay. How we can change the design or operational parameters so that some of these errors may be minimized, so that we can avoid them or neglect them without considering in the design of the capillary viscometers. So, that is the next step. So, if you have a cross section area of barrel very much larger than the cross section area of capillary, then what will happen? Effect of variable head and then fluid friction in the barrel can be neglected. So, that design point of view, you make such kind of thing. That is true also most of the cases. Barrel diameter is very much larger compared to the capillary diameter. Capillary may be 1 mm, 2 mm diameter only in general you prefer to use, right. So, at the max 5 mm capillaries you try 5 mm diameter capillaries you may be using, but barrels you may be having like diameter something like 50 centimeters or 20 centimeters, something like that. So, obviously this is taken care in most of the capillary viscometers by default without making much changes. But of course, if such conditions are not maintained in the designing, so then you can try to have this point into the consideration. Then operate viscometer at flow rates where the changes in kinetic energy of emerging stream from capillary are negligible compared with other terms in the mechanical energy balance. You can do the mechanical energy balance for the barrel and then for the capillary. You can cancel out the term such a way, or you can have the flow rate such a way that the kinetic energy losses because of the fluid emerging from the capillary is very much small compared to the other terms in the mechanical energy balance, right. So, that is the other thing. So, after this most of the things have been taken care. What are the things have been not taken care? End effects we cannot avoid, we have to do some corrections. Slip effects we cannot avoid, we have to do some corrections. And then in addition to this one, so called deviation from laminar flow. Deviation from laminar flow, that also you can avoid by operating such a way that your flow rate is under the laminar condition, but you do not know. So, that is the reason we will be seeing a few discussions like from Q versus delta P information, can we have a kind of a priori can we have a kind of intuition whether the flow is in the laminar or in a turbulent condition. That is the other one we are going to see. So, remaining lecture we are going to discuss on end effects. In the next lecture we will be discussing on wall slip effects and then deviation from laminar flow conditions. Viscous heating we are not taking into the consideration as of now. End effects. So, at the entry of the capillary tube, flow is not fully developed and then pressure drop increases because at the entry the cross section area, flow cross section area suddenly contraction has taken place. So, then because of that one obviously pressure drop would be higher at that entry point as I just explained, right. So, contribution of, and further the contribution of exit effect, whatever the at exit the pressure drop is usually slightly smaller than the fully developed flow pressure drop. So, that is not going to affect much in the overall rheology. So, that exit effect may be neglected. Exit effect in the end effects, overall end effects may be negligible, but entry effects cannot be neglected. So, then we have to do appropriate considerations. So, magnitude of entry effect depends on nature of the non-Newtonian fluid that we are doing. So, but whatever the things that we are going to see now, they are primarily for time independent non-Newtonian fluids. For generalized Newtonian fluids or time independent non-Newtonian fluids, if you have L by D more than 100 or 150, it is more or less these end effects are taken care, and then you can be safe. You do not need to worry about these end effects. if you are maintaining L by D more than 100 or 150. But for the other fluids like viscoelastic materials, even 200 may not be sufficient, and there is no concrete data available how much L by D value is sufficient for viscoelastic fluids, that is not known yet. Okay. But it has been observed that even L by D 200 or more may not be sufficient to avoid end effects in the case of viscoelastic materials when they are flowing through capillaries. Okay. So, now correction for end effects. Now, we understand that at the entrance or at the entry point, the pressure drop increases because of the sudden contraction of the flow area, right, from which the material is passing through. So, there is a pressure drop increase. So, how much pressure drop has increased because of the such sudden contraction, that we have to estimate, and then that amount we have to subtract from the delta P information that we are getting from the experimental data. Okay. So, that is what we are doing. So, why it is required? Because often it is not possible that you can have large L by D ratios. Okay. So, obviously having some kind of correction methods to make a correction. Let us say you have only one single capillary, and then when you are measuring L by D of that capillary is around 70 or 80 only. So, it may be difficult to have a reliable rheological information from such small capillaries. Then what we do? Obtained shear stress values must be corrected for end effects. Now, we can safely say rather end effects, entry effect we can say, because exit effects are negligible. Okay. So, Bagley suggested an approach for corrections in the pressure drop, so that pressure drop correction is when you taken care of that pressure drop, increased pressure drop, and then subtracted from the pressure drop of experimental information. So, then whatever the shear stress that you get, that is not going to be different from the that is going to be reliable, that is going to be true shear stress. Otherwise, also simply how do you understand whether the obtained this information Q versus delta P also, you can simply do different you can get the Q versus delta P information by using different capillaries of different L and different D, and then you plot all of them. If they are not superimposing onto each other or if they are not close to each other, so then that means they are incurring some kind of error in the rheology. So, that is what the simplest way that you can understand without going into the details whether the end effects are there or not, or wall slip effects are there or not. If any error is there, so then this information is going to deviate even if you are maintaining the large L by dV ratios also. So, Q versus delta P data can be obtained for several at least 3 tubes of same diameter, but different lengths like L1, L2, L3 and so on. So, minimum 3 are required. The condition is that if you wanted to find out the correction for end effects, you have to have at least 3 or more capillaries of different lengths, but the diameter has to be same. Because if you change the diameter, so then wall slip will also come into the picture. So, you cannot handle 2 errors at a time, or even if you try to do, there may be some kind of errors. So, what we do? We take one by one. Okay. Now, whatever 3 capillaries you are using, that means you are taking a barrel like this, and then different capillaries of, and then you are maintaining same diameter, but different times you are taking different length capillaries, sometimes L1, sometimes L2, next time maybe further larger L3 capillary, like this you are taking. Diameter you are keeping same, and then you are trying to get the Q versus minus delta P information for each of 3 cases. So, that if you plot measured pressure drop, that is delta P minus delta P versus flow rate, if you plot, then you can have different lines like this. Different lines you may get if that length is not sufficient. If you have even the lowest length, whatever the capillary you have taken, if it is sufficiently large value, so that L by D is more than 100 or 150, then all 3 lines may be very close to each other, merging onto each other also, superimposing onto each other, that is also possible. Since the length is not sufficient, so then you get 3 different curves like this. Okay. So, then well, with increasing length what you see for a constant flow rate, the pressure drop also increases. That is what you can understand with increasing the length. Now, what we do, this volumetric flow rate information, you get velocity from here, and then from this velocity what you get 8 V by d. So, for each flow rate what is the corresponding 8 V by d, and then you draw a line here and then you measure what is the pressures. That information that you can you may require for further calculations. So, then interpolate either by fitting a second order polynomial or by using graphical approach to obtain a series of minus delta p versus L points for a range of constant values of q. Different q values you take and then replot the data or interpolate the data and then get minus delta p versus L data points. Then you plot this minus delta p versus L data whatever by interpolation you have got it or by graphical approach. So, that you plot for different q values. Q values corresponding to q is 8 V by d. So, why 8 V by d? Because we have to do 8 V by d calculations anyway again. So, for that 8 V by d, so let us say 8 V by d value, pressure drop versus L information whatever is there. So, that you are plotting here like this, right. So, another 8 V by d for different L values you may get this curve like this. Another 8 V by d for different L values you may get the minus delta p information like this, minus delta p versus L for different 8 V by d values you get different curves like this, because L is not sufficiently large enough. If it is a lengthy capillary, then here again you may be getting the same lines or superimposing onto each other, or these lines are very close to each other. Then what you do? You extend these lines to L is equals to 0 curve or to get the intercept on the y axis. So, these intercepts are nothing but they will give the whatever that extra pressure or increased pressure at the entry point is there, that extra pressure you get from this point, from these intercepts. Okay. So, linear dependence of minus delta p by L is often found, but not necessary for all cases. That also depends on different situations. Then extrapolate to L is equals to 0 to obtain entrance correction for the pressure drop. So, minus delta p for each value of 8 V by d. Then from whatever the measured pressure drop, you subtract this minus delta p e for each 8 V by d, for each 8 V by d, then you get this whatever the pressure correction, right, whatever this pressure correction minus delta p c that you get, that you will be using in your tau w calculation, minus delta p c L r by 2. In this equation you will be using this one, delta p c you will be using rather than delta p. Okay. So, for fully developed condition the corrected pressure would be minus delta p c, that is nothing but measured pressure drop minus this whatever the entrance correction for pressure drop minus delta p e. So, if you subtract minus delta p e from the measured pressure drop, you will be getting corrected pressure drop for fully developed flow condition, that you will be using for your tau w calculations. It is a bit lengthier, but simple process. Right. Now, we take an example problem so that to understand how to do this one, otherwise it becomes difficult to realize without doing an example problem. Okay. So, before taking example problem, we see what are the drawbacks of this approach. Okay. First of all, may not be possible to carry out test using capillaries of different lengths, but same diameter. It is very difficult to get same diameter different capillaries, different length capillaries. Also, it is very cumbersome. And then some studies reported whatever this minus delta p versus L curve, that previous slide that we have seen. So, you may not get the linear line, straight line you may not get, sometimes you may get the non-linear curves you may get. Okay. That is another problem. And then that problem is coming maybe because of other errors like wall slip, time dependent behavior, fluid may be having time dependent behavior, there may be viscous heating, and then viscosity may be pressure dependent, because all these things are pressure is involved. So, the fluid viscosity is sensitive to the pressure difference. So, then again that is also leading to some error, and then altogether making this minus delta p by L minus delta p versus L curve non-linear. Okay. So, sometimes capillary too short for flow to be fully developed flow, right. This pressure dependent viscosity causes positive deviation from straight line behavior even when L by D is large, whereas the wall slip thixotropy in the sense time dependent fluid behavior and then viscous heating, these three may be leading to negative deviation from the pressure drop, right, and then the pressure dependent viscosity may be leading to positive deviation from the straight line, not the pressure drop, straight line behavior. Okay. So, now the example problem. So, following experimental data has been obtained for a polymer solution of 4% CMC in water using an extrusion constant flow rate rheometer. The diameters of barrel and capillary are 23.3 and 0.408 mm respectively. Barrel diameter is 23.3 mm, capillary diameter is 0.408 mm. Okay. So, that the data is given in terms of velocity of ram or barrel velocity, whatever in the fluid that velocity is said, that velocity is given, that velocity versus pressure drop information is given when you use different length capillaries. Diameter you are keeping same, but length you are changing. Once you are taking only 49.5 mm, next time you are taking 74.5 mm and then 99.5 mm next time, right. So, now obtain the shear stress shear rate information for this polymer solution. So, we have to obtain the true shear stress to true shear rate information, not the nominal shear rate information. Neglect the friction in the barrel, one source of error, it is already stated in the problem that we can neglect, and then establish magnitude of end effects. Okay. So, that is what we are going to see. Since obviously the data information whatever is given, that is given for the 3 different length capillaries, but of same diameter. So, it is possible to establish entrance effects, right. So, that is what we are going to see. So, we have seen that nominal shear rate is nothing but 8V by D, but V is not given, V is not given, V ram is given or the barrel velocity is given, right. V is nothing but the average velocity of the fluid when it is passing through the capillary, not in the barrel. So, that we have to find out. Average velocity V in the capillary is obtained by using continuity equation, that pi dB square V ram by 4 is equals to pi d square V by 4. dB is nothing but barrel diameter, d is nothing but capillary diameter, V ram is nothing but the velocity of the fluid in the ram that is given, V is nothing but average velocity of the fluid in the capillary. So, this V we have to find out. So, let us say for the first data point, V ram is nothing but 0.09, is not it, right, that is given, and then dB barrel diameter is given as 23.3 mm, D that is capillary diameter 0.408 mm, that is also given. So, this pi by 4 is cancelled out. So, V is nothing but dB square by D square multiplied by V ram, that is given 0.09 mm per second. So, in meters 10 power minus 3 is there. So, then overall you get V average or V in the capillary, average velocity in the capillary is nothing but 0.294 meter per second. This is for the first data point. So, gamma dot Wn, N stands for here the nominal or apparent shear rate, that is nothing but 8V by D. So, V just now you got it for the first data point, D is given. So, then 5755 second inverse you will get nominal or apparent shear rate. This is not the true shear rate, it is the nominal or apparent shear rate. It is true shear rate if it is a Newtonian fluid. If it is a time independent non-Newtonian fluid, it is not a true shear rate. We have to make that correction 3n prime plus 1 by 4n prime. All that also we will be doing, and then tau W is nothing but minus delta Pc by L multiplied by D4. Now, we are taking the corrected pressure because we have to find out entrance effect. If the entrance effect is not there, so all that pressure information for different capillary lengths L, L1, L2, L3, you may be getting same pressure drop, but that is not true. So, first capillary of 49.5 mm length, Vram is given as 0.09, corresponding V average for the capillary is 0.294 meter per second, just now we have found it, and then 8 V by D, corresponding 8 V by D is 5755 second inverse, and then delta P for the first capillary, first Vram value is 44.8, 448.16 kilopascal, that is also given. So, similarly, for the same first capillary of 49.5 mm, you obtain the Vram is given. So, corresponding V average or capillary velocity you find out. So, then corresponding nominal shear rate you find out and tabulate them here, and then measured pressure drop. This is measured, this is all measured pressure drop that is given, so that you just note down. Similarly, for the second capillary and third capillary also you can see. So, you can see the shear rates, they are given like exactly same. Actually, you do not get exactly same, but you get very close to each other when you do the calculation. So, then I have done the average kind of thing and then made it to the round figure. So, then these values are given, but they are very close to each other. Okay. So, such kind of averaging for the pressure I cannot do, because see pressure for the, when one capillary you are using 49.5 and then you are maintaining the capillary velocity 0.294 meter per second, what is the pressure drop is required for the first capillary is 448.16 kilopascal. For the second capillary, to maintain the same velocity, capillary velocity, you need 655 kilopascals. To maintain the same capillary velocity again, if you use further longer capillary of 99.5 mm, then you are getting, you required to provide 882.5 pressure drop, kilopascals of pressure drop you have to, 882.5 kilopascals of pressure drop you have to provide to get the same capillary velocity for a longer capillary. So, then these are very different, from L1, let us say if you take this one L1, this one L2, this one L3, from L1 to L3 it is almost becoming double. So, we cannot take that averaging. So, that why it is coming, because of the entrance effect. So, then we have to find out delta PE. So, now what we do for each value of this thing 8 V by D. So, let us say first value of 8 V by D is 5755, then corresponding L value. So, let us say when L is 49.5, what is the minus delta P, measured pressure drop is 448.16. For the same 8 V by D of 5755, but L is 74.5, then it is 655. Then again same 5755 of shear rate, but L is 99.5, then what is the corresponding pressure drop, measured pressure drop, 882.5 kilopascal. Like that, this is the tabulation. So, this is 8 V by D, this is L, this is minus delta P. So, similarly for other 8 V by D 7676, you have to do like that. Likewise, 95, 96, 13, 4, 3, 4 and then 15, 3, 5, 3, like this you have to have these things. Why? Because next what we are going to do, we are going to plot minus delta P versus L for different 8 V by D. For that reason we need to do this one. Okay. So, that when you arrange, when 8 V by D is 5755, for different L values given pressure drop is this one, measured pressure drop this one. So, other 8 V by D similarly you have like this information. So, whatever the previous slide you have calculated, that we have rearranged here, we just rearranged here, because for each 8 V by D we wanted to plot minus delta P versus L. When you plot, you get the curve like this, different curves you get like this, and then you extend these curves to L is equals to 0 point. right. So, L is equals to 0 when you extend or extrapolate. So, then you get this minus delta P E for each 8V by D. So, for the first 8V by D of 5755 second inverse, what is minus delta P E? You get 14.6. So, this 14.6 if you have to subtract from 448.16. So, then you get 433.56. Then also from 655 you have to subtract this 14.6. So, then you get 640.4 delta Pc for the second capillary. For the third capillary again from 882.5 you have to subtract this 14.6. So, then you get 867.9 for the third capillary. So, these are the corrected pressures delta Pc. Okay. So, this delta Pc you will be using tau w is equals to minus delta Pc by L multiplied by d by 4 or r by 2. So, like that for other values of 8V by D you find out what is minus delta Pe and then what are the corresponding delta Pc values. So, let us say first data point, if you take 8V by D 5755 second inverse delta Pe we got 14.6 kilopascals. So, corresponding tau w would be 448.16 minus 14.6, that is nothing but 433.56 kilopascal. So, 10 power 3 then multiplied by D is nothing but 0.408 mm capillary multiplied by 10 power minus 3. So, you get meters, and then L is nothing but for the first case 49.5 mm first capillary. So, then that is how much it will be into multiplied by 10 power minus 3 you are doing, because it is given in mm. So, we are getting in meters, divided by 4 is there. So, as it is. So, you will get 893.4 pascals. You will get 893.4 pascals corresponding to this point actually. So, likewise if you do for all other cases, you will get for different capillaries you get tau w values like this. Now, you see when 8V by D is 5755, right, even if you change the capillaries of length of the capillaries after incorporating the correction, what is the tau w that you can see? 890, 875, 890 like that. So, they are almost same, they are not exactly same, but they are very close to each other. As I said, this 8V by D is also exactly, they are not same, they are close to 5750, 5760 like that, they are close to each other. So, then we have done the averaging and written like this. So, tau w also after incorporating this correction, what we get? This tau w values, even if you are changing L value, they are not changing, because we have already incorporated that correction, that is subtracted minus delta Pe information from the measured pressure drop information. Okay? That is it. So, this is how we have to find out. So, now again what we do? We do the averaging of these 3 values and then write it as one value here. So, we have average tau w is 886, 970, 1041 and then 1139, 1153 for different 8V by D values. Okay. So, length effect is entrance effect has been taken care. So, now true shear stress you got, this is true shear stress only. Okay. This even this also true shear stress, but we have taken average over all 3 L values. So, that is because averaging, because they are very close to each other, even if you take one case, that is also not going to affect anything on the rheology. But shear rate also we need to have true shear rate. So, what we need to have? We need to have this correction 3n prime plus 1 by 4n prime we need to have for each case, right. N prime is nothing but d log of tau w divided by d log of 8V by D. So, for each 8V by D tau w information you already got. So, that you plot on a log scale, you plot tau w versus 8V by D, then you find out n prime. So, that n prime you will get, that n prime is nothing but 0.275. That means the material is highly shear thinning. The material, whatever the 4% CMC in water, that solution you got, that is highly shear thinning because its N prime value is very small, 0.275. Now, you get 3 n prime plus 1 by 4 n prime and then multiply that correction with the corresponding 8 V by D value. So, then you get true shear rate information, this one, right. This is how you have to incorporate corrections for the entrance effect in the capillary viscometer, if at all, if you do not have a sufficiently large L by D capillaries. References for this lecture: the entire lecture is prepared from this lecture, from this reference book by Chabra and Richardson. However, similar information you may also find in the remaining reference books. Thank you.